December 1928, a white-coated researcher slices into a cat's brain, hunting for a fixed map of every connection. He found chaos instead. The old dogma claimed the brain stops changing after 25, based on flawed studies of young animals. That dogma was wrong. It shaped treatments, education, and entire careers for decades, all built on sand. Then came the scanners. Functional MRI images from the 1990s lit up with unexpected activity in adult brains. New neurons were growing. The hippocampus, a memory hub, showed activity far beyond what textbooks predicted. Plasticity never ended. It simply slowed down, waiting for the right trigger to speed up again. The critical period was not a locked door. It was a gate on a hinge, ready to swing open with effort and repetition. Any age could push it open. Force the brain to change. That question drives entire research fields, from stroke recovery to skill acquisition. What happens when we force it to rebuild? October 1998, a lab in California watches a single neuron fire, then fire again. They're tracking the electrical spike across a network of cultured cells, measuring the gap between signals. The connection gets stronger. That's synaptic plasticity. The brain learns by strengthening certain pathways. It prunes the branches it doesn't use and grows new ones. Your brain loses about 1% of its synapses every year after age 20. But the pruning process itself creates space for new learning. Without it, you'd be stuck with childhood patterns forever. Then comes the wrapper. Myelin, the fatty insulation around nerve fibers, speeds up the signal. A myelinated neuron fires 100 times faster than an unmyelinated one. Every time you repeat a movement or a thought, your brain wraps a little more myelin around the active circuit. It's like laying down a superhighway over a dirt road. But myelin is stubborn. You have to fire that circuit over and over before the insulation thickens. Repetition is the price of speed. Now the chemical messenger. BDNF, brain-derived neurotrophic factor, seeds new neurons and keeps existing ones alive. Think of it as fertilizer for the brain garden. When you exercise, your body pumps out more BDNF. But BDNF levels drop with age and stress. The good news? You can increase BDNF with effort. Intense exercise, cold exposure, and intermittent fasting trigger its release. The brain responds to stress by building new parts. But there's a deeper layer. Adult neurogenesis, the birth of new neurons, happens in the hippocampus. Scientists used to think it stopped after childhood. They were wrong. New neurons grow every day, even in your 70s. But they must earn their place. Only the ones that connect to active circuits survive. Your choices determine which neurons live and which ones dissolve. So the gate swings open. But it doesn't swing by itself. The biological mechanisms are in place. Pruning, myelin, BDNF, new neurons. They're all waiting for the right signal. That signal is attention. Focused, deliberate attention. Without it, the machinery sits idle. The question isn't whether you can change your brain. It's whether you'll pay the price to do it. A screen in a Stanford lab flickers with a checkerboard pattern. The subject watches for 60 seconds. Then the pattern vanishes. That triggers a burst of plasticity. Huberman calls this the visual trigger. It opens a window of neurochemical readiness. Plasticity demands a trigger. Without that initial pulse of attention, the neural circuits stay locked in their old patterns. So we force the door open. Now the next step. 90 minutes. That's the natural attention span of the human brain. Huberman recommends working in 90-minute blocks, then taking a 10-minute break. No phone, no distractions. The brain needs that rest to consolidate. Then comes deep sleep. Sleep isn't just rest. It's the editing room. During deep sleep, the brain replays the day's learning, strengthening the new connections and pruning the old ones. Without deep sleep, plasticity vanishes. So here's the protocol. Visual trigger, focused work, deep sleep. One leads to the next. But what happens when you skip a sleep? What if you train, but never rest? The brain holds the new pattern. But only if you sleep. A 70-year-old woman picks up a ukulele for the first time. Her fingers fumble over the strings, pressing down wrong notes for weeks. Then a chord rings clear. That's neuroplasticity in action. The old brain doesn't stop growing. It just needs a different kind of push. Stroke survivors prove this every day. A man loses speech after a clot hits his left hemisphere. He relearns words by singing them, rerouting language through the right side of his brain. That rewiring takes months of repetition. But it happens. Perineuronal nets are the culprit. These jelly-like webs wrap around neurons, locking them into place after childhood. They act like plastic wrap over a finished sculpture. But research shows they loosen with age. A 2019 study from Stanford found that removing a single enzyme in mice dissolved those nets. The old mice learned mazes as fast as the young ones. Humans don't need enzyme injections. We have a natural solvent. It's called focused attention. When you concentrate hard on a new skill, the brain releases enzymes that chew through the perineuronal nets. The nets thin out. New connections sprout. A 60-year-old learning Mandarin in Beijing proves this. Her brain scans show fresh dendritic spines forming in the hippocampus after 6 months of daily practice. The nets don't vanish completely. They just become less rigid. So age isn't a wall. It's a gate that needs a heavier key. What happens when you stop turning that key? A clock reads 6:14 a.m. A woman sits at a desk with a cheap notebook and a timer set for 90 minutes, her coffee cold and forgotten. This is the laboratory. Her task is deliberate practice. She picks a single skill, say learning a new piano chord, and repeats it with focused attention, catching every mistake in real time. No multitasking. The brain's plasticity demands a narrow beam of concentration. Diffuse attention builds nothing but fatigue. That's the first pillar, attention. Then comes novelty. She doesn't just repeat the same chord every day. She changes the key, the tempo, the hand position. She forces the brain to build new connections, not just strengthen old ones. The second pillar, novelty. The third pillar is the hardest to sell. Sleep. She closes the notebook, sets down the timer, and walks away. Recovery is not laziness. It's the moment when the brain replays the day's practice, filing away the new patterns into permanent memory. Without sleep, the practice evaporates. So the routine is simple. Attention, novelty, sleep. But the woman at the desk has a job, a family, a life that pulls her away from the timer. She skips the sleep. She skips the novelty. She sticks to the same routine. What happens then? The brain stops changing. The neuroplasticity window slams shut. The practice becomes a dead habit, not a living skill. So the question is not how to build a practice. It's how to protect it. The woman stares at the sticky notes. She knows the answer. She just doesn't follow